Welcome back to EDGEcast, the series where we show you tips, tricks, and best practices when using Solid Edge. In this episode, we'll be exploring the basics of using Synchronous mode to create and edit sheet metal parts in ST10. While many CAD packages provide sheet metal functionality, Synchronous mode in Solid Edge is very different. In case you're not familiar with either Synchronous mode or the working principles behind sheet metal modelling, I'll give a brief explanation here. Then I'll head straight into demonstrations. Synchronous mode is very intuitive, so it's easier to explain while showing you what's possible with flange creation, then creating what we know as procedural features, and we'll also be showing how to control sheet metal features without the need to edit two-dimensional sketches. I'll also show some design in the context of an assembly, creating a sheet metal cover for an existing assembly, all while using Synchronous mode. Finally, I'll show how to export a flat pattern from a 3D sheet metal file, how to switch rapidly between sheet metal and part environments, and how you can edit a sheet metal part designed in another CAD package as if it were created natively in Solid Edge. To start with, it's probably best to answer the question, what do I mean when I say I'm working with synchronous sheet metal? This means two things. The first is that instead of creating a part file, I'm creating a very special type of file that obeys different rules. For example, sheet metal parts are typically designed as already bent into their final form. They also have a unique thickness rule. In addition to this rule, all bends in this material can be flattened with a mathematical operator that relies on the material properties of the sheet metal in question. This means that, when flattened, the virtual sheet metal material behaves like it would in real life, providing accurate dimensions for the machined blank. Secondly, the synchronous part of synchronous sheet metal means that the parts and their flanges do not rely on sketches for their definition. They can exist and be edited without them. This also means that there is no order of feature importance. The first flange on a part could be deleted, and leave all the features around it still visible. This lack of direct sketch dependency might suggest that this is direct modelling, but that's not the case. Unlike direct models, synchronous models can be driven by dimensions, relationships between 3D faces instead of 2D sketches, and what we call live rules. If you'd like more information on how synchronous mode works in the normal part environment, I'll leave a link in this video's description to an older EDGEcast episode. So now we've discussed a little of synchronous theory, let's put that information to use. It's time to create a simple sheet metal part, and rather than my normal part template, I'm going to create a new part with sheet metal. Your templates might be called something different, but the image should look similar. The sheet metal environment should look familiar if you've used synchronous mode before to make parts. We have our sketch commands, geometry creation commands, and dimensions. And just like in the part environment, we need to start by placing a sketch. The part I want to make is a mounting bracket with 5 flanges, and I'm going to use a very liberal sketch to create my first synchronous feature. And if you're yelling at your screen right now telling me to trim my sketch corners, this video is definitely for you. Because after I'm finished, all I'll need to do is hold down Control and click, and then keep left-clicking on these 6 sketch regions until they're all highlighted. Then I can extrude material, but only by a certain distance. 1mm is enough for now. And my sketches aren't useful anymore. They've served their purpose, so I'll hide them. In sheet metal, the material being used and its gauge thickness is arguably more important than it is for normal part files. So I'll assign that as a next step before making more features. Aluminium 1060 should do. And we'll use 20 gauge, or just under 1mm. Should give us a nice light bracket. If needed, this can change later on. One thing that often confuses new users is how to place a flange when, as you can see, there is no flange command on the ribbon bar. Instead, if you click on a sheet metal edge, these white arrows appear. This is the synchronous steering wheel, and if you're not familiar with it, I highly recommend watching my steering wheel EDGEcast episode, once again linked below. If I click on the larger arrow, this face will start moving to extend the tab. And if we zoom out, the other 3 tab faces also move, because of live rules, which we'll touch on later. But if I choose the shorter arrow, this starts the synchronous flange command with added material following your mouse, and 2 input fields for distance and angle. But 1 flange? That's far too simple. Instead, I'm going to hold down Control and click on 4 edges, start the flange command, and then create 50mm flanges from each of them in the same direction. With this bottom edge, I'll repeat the process, but instead I'll use the Tab key on my keyboard to switch to the angle field and enter a different value. 135 degrees for a 45-degree angle between it and the back of the main tab. I also need 4 mounting holes and a dimple in the middle of the part to ensure it resists bending around the x-axis. The hole command works exactly as you would expect in the part environment. Hover over a face and press F3 to lock onto it. I personally like using Ctrl and H to view the face at 90 degrees. Which holes are the most appropriate? Let's go into the hole table. M12 is the default. I can always change that later. For the locations, I'll use midpoints from 2 edges for each hole. I'll hover over 1 midpoint, and then another midpoint, and now the hole can snap to each midpoint. Left-click to place the hole once your mouse is in position, and then find the next 3 locations with exactly the same method. If I cared about accurately dimensioning their positions, I would add dimensions in 3D, but that can be done later, so I'll finish and place my dimple. Now in synchronous mode, there's a prerequisite for a sheet metal dimple. A sketch region needs to exist already. In this case, I'll use a rectangle, and the dimple can be made about the base coordinate system. 15mm width by 60mm height looks okay for now. Now we can start the dimple feature. Select the region and reverse the direction for the dimple direction, because this is not what I want. That is, though. And I'll stick with default options for dimple creation for now. If you remember, I mentioned that synchronous features did not depend on sketches for their definition, but dimples are an exception to this rule. Just like the slot feature, they have an internal profile which you can edit by selecting them and clicking the callout that appears, and then Edit Profile. In this case, I'll add 5mm fillets to each profile corner, just to soften the dimple. At which point I'll accept with a green tick, and press Escape when I'm happy. Sheet metal parts often have sharp corners on them, and best practice is to break or round them off for safety reasons. In this case, I want to add fillets to each corner in the model. And if I wanted to do so individually, I could, but instead, I'll fence select all the corners that I want to break. And instead of 10mm, I think a 5mm break would be more suitable. I have almost all the flanges and other features that I need in this part, so now I'll start controlling its shape with dimensions. Rather than having features controlled by sketches, synchronous models have features controlled directly by dimensions in 3D. Smart Dimension allows 3D points to be dimensioned to each other, and if I dimension this edge, the inside vertex of the 2 bends are picked up. But if I select the outer edge, the dimension is between the 2 outer points. In other words, the 2 outside faces are now made 150mm apart. To change this, I can edit the dimension value and lock it with this little padlock symbol if I wanted. When I do this, or alter the value, the faces that can move during a value change are highlighted light blue. The bottom flange now needs a jog in it, but this also needs a sketch. But to create a jog, all I'll need is 1 line. In this case, a straight line 25mm from the bottom edge of the flange will work. Once again, I don't care about sketching neatly, as the sketch is just going to be hidden after it's used to create the feature. So I'll start the jog command, and the white arrows here indicate which side of the jog is going to be moved. In this case, it's going to be the lower side. Let's extend the material by 25mm. In real life, this would stretch the material, but solid edge sheet metal parts will never get any thinner while being edited. Sheet metal parts have bends in them, as you may know, and by default bends have a radius assigned by their material properties. However, this can be overridden by selecting a bend, choosing the radius callout, and then entering your own value. However, I'm not happy with the angle this entire jog's been modelled at, so let's move it. If I fence select the two flanges from the right view, and also the bend, I can drag my steering wheel to the bend point, here, and rotate all the selected features around it. Let's increase the angle. Let's say by 15 degrees. Alternatively, if you know which features on the feature tree you want to angle or move, you can select them from here and carry out the same move commands. Rotating this flange, however, also moves all the other three flanges inwards because of the active design intent live rules, which can tell Solid Edge which faces to move in addition to the ones you already had selected. In this case, the symmetric live rule is active, in this box here, as the part was created symmetrically about the base coordinate system. It's almost like having a mirror feature in place. Pressing S will toggle this live rule off, meaning that only the two flanges on the left move. This happens because they are considered coplanar to each other, with faces sharing the same 2D plane. This can also be overridden either by unchecking the coplanar checkbox or by pressing C on the keyboard, which will toggle it on and off. Once we've done that, now the flange can be moved independently of the others. So those are live rules in action, but users can also program in their own design intent with relationships between faces. The flanges of the bracket have a particular offset between each other, and I'll say that I want that offset to be maintained without the need for a dimension. By using the offset face relate command, it's possible to choose this edge, accept, then choose another face, finish, and if we move one of those faces, the offset will be maintained. Even better, if coplanar design intent is turned on, let's do that by pressing C to check the box, the offset is maintained for both sides of the part when I move just one of these faces. So as you see, there are three main methods of introducing intelligence into a synchronous model: dimensions, face relationships, and intelligent use of live rules. Sheet metal parts can also be created while in an assembly, which is useful if you need to make a guard, say, to fit around moving parts. In this case, I'm going to use a demonstration set very kindly provided by Master Mover, one of our customers. This particular mover is only partly finished, and is missing a guard around its hydraulic cylinder and lines. That means that we can create a part in place with this command right here. The template I'm using is already selected as the ISO sheet metal part, and for the material I'll use aluminium. The position for the base coordinate system here isn't very important, but I'll place it in the middle of the assembly and save the part as cover. This puts us into the edit in place environment. So let's make a sketch on this plane here. You'll notice I'm editing a part, but I can still see the assembly while I'm doing it. Now the end goal is to make a sheet metal part that completely covers this assembly with an arced flange and two straight flanges 50mm long. So I'll be making this open sketch, because after I'm done, I'll need to make a contour flange, which creates material at 90 degrees to a sketch profile, which is the one I just created. I could either extrude one direction like this, but instead I will press Shift once and create material in a symmetric fashion. How far should we go? Well, because we're editing in the context of the assembly, we can select an existing assembly keypoint, like this one right here. After that, we can create additional flanges from the part, so that it fits onto the assembly better, using the synchronous tools we've already become familiar with, such as creating multiple flanges at once. There are still a few edits that would need carrying out, but we're a little short on time today. For more information, I'd advise watching the Synchronous Modeling EDGEcast episodes, or enrolling for one of our Synchronous training courses. Now, Solid Edge models sheet metal parts as already fully formed, But in real life, you need a flat piece of material to bend into shape, and unless you're an experienced technician, you might need to do some bend calculations for the more complex parts. But computers are much better at such calculations than humans, so we'll just ask Solid Edge to calculate the flat pattern for us, using the equation you can see right here. Bear in mind that you can only create one flat pattern per sheet metal part, and it's stored in the part file definition. It doesn't create a separate file. Under the Tools tab, next to the Synchronous and Ordered buttons, you'll find the Flatten button, which starts up the Flat Pattern command. This is normally only a two-step process, the first of which is to click on a face that's going to be oriented upwards in the pattern. In this case, it's this one right here. Then we need to click on a straight part edge to define the x-axis of the flattened part. And if you look closely at the edge being highlighted, there's a small dot at one of the ends, closest to my mouse. This indicates the x-axis origin point in the flattened part. If I click while the mouse is in this position, the part's going to calculate every bend equation present and flatten itself. Conveniently, it also tells us the size of the blank body required to make it. Parts can also be converted to sheet metal geometry on the fly. There are a few reasons why you may wish to do this. Sometimes parts can be completed, but then a request might be made to model them in a different material. Perhaps a moulded ABS cover would need to be made in sheet metal aluminium instead. Other users prefer to model the overall shape of their part in the part environment, thin wall it, and then convert it to sheet metal later down the line. If you do so, any holes and cuts will maintain their position on the new sheet metal model, as you can see in the screenshots right here. To show this in action, here's a thin-walled part I made earlier. It was originally made in polycarbonate, but now it needs to be stainless steel for some reason. So, I'll go into the Tools tab, select Thin Part to Sheet Metal, and choose a flat face to act as a base tab for the new part. Now there's a warning here saying that the part can't be flattened, and that we need to open up some edges with the Rip Edges command. Now the problem with this is that the 4 vertical edges are stopping the part from flattening. However, this is the button we need, Rip Edges, and because there are a few different possible flat patterns, we'll need to select the edges to rip manually, and then accept our selection. Now here we are with a sheet metal model, and where there were previously right-angled corners, we have these lovely sheet metal corners, which can be closed if necessary. The only thing we need to do now is change the material to stainless steel. And just to make it obvious that it's a sheet metal box, I'm going to go to the View tab and turn on Single Color Edges, which I have set to black. Finally, we'll do what we always do with sheet metal parts and flatten it, using the same workflow as before. And just like that, it's ready for drafting. So, now that you know how the basics of sheet metal work, I'll show you something that might save quite a bit of time, and that's working with third-party geometry. While most CAD packages can open parts made by other software and add features, editing the features that are already in place can prove quite difficult. However, Synchronous mode allows imported solid parts to be edited as if they had originally been created in Solid Edge. I'm going to open up a sheet metal file, and let's assume it was made by another user. We're going to be opening it in Solid Edge, but as you can probably see, this isn't a Solid Edge part, but a SolidWorks part. As Cutting Edge is a Siemens reseller, I have all of the translators available for Solid Edge, and I can open up SolidWorks files that were created before a certain version directly. But if you don't have those translators, you might have to use step or parasolid translators. The workflow is pretty much the same though. After the translation is finished, you might notice that the part has been brought through as a single part copy, with no features available. However, if I select my Tools tab, and then choose the Thin Part to Sheet Metal command, it's going to start up this command bar, which you might recognize from before. Now I need to choose a base tab for the sheet metal conversion, which is usually the biggest one. And because we don't need any further edits to be made to make the part obey sheet metal rules, all the flanges are individually recognized. It hasn't recognised the material from SolidWorks, as I didn't use my data migration tool, but I'll assign my own solid edge material and gauge thickness. I think 1060 aluminium, and 12 gauge, why not? And do I want to replace the face styles? Yes, I do. Maybe 12 gauge was too thick. Perhaps 20 gauge would be more suitable. I don't want to over-engineer this component. So, that's all set up. But you'll notice there are some mounting holes here. In SolidWorks, these had built-in intelligence, but SolidWorks holes can't be read in Solid Edge, and these are now just dumb cylindrical faces. So, do I have to delete and remodel them? Well, no. Synchronous mode provides a Recognize Holes tool in part and sheet metal environments, so let's run it. It thinks there are 4 simple 2.44mm holes in this part, and if I hover over the line in the table, it highlights their location. Now, if I was happy with this, I'd click OK, but I'm not. These aren't meant to be just holes. They need to be from my isometric hole table, as I know for a fact my production staff have only the tools to match that table. And they don't have 2.44mm drill bits, but, as luck would have it, they do have 2.45, and I'm not working to particularly high tolerances with this part, so I'll say that's fine. And if I hit OK, my holes now appear in the feature tree as hole 1, which will be 2.45mm diameter holes. Face relationships can be applied exactly as you saw with the earlier part, meaning that this imported part can be completely controlled with combinations of dimensions, live rules, and face relationships, just like a normal synchronous model. In summary, we've seen the basics of synchronous sheet metal part creation. There's far too much to go through in a short video, but we covered feature creation, materials, and the 3 main ways of controlling a synchronous model: dimensions, face relationships, and live rules. We also saw how to generate a flat pattern for production drawings and convert a thin part model to sheet metal. Finally, we covered how to import sheet metal geometry from other CAD software, such as Step or Parasolid, and make it obey our commands and edits. Thanks very much for watching, and if you have any questions, different areas of Solid Edge you'd like us to cover in the future, or other feedback, please either leave a comment below or send them to us by email at support@cuttingedge.co.uk. And be sure to tune in to watch the next episode of EDGEcast, where I'll be showing you how to use assembly display configurations effectively.